Okay, so we're going to look at our first example of evaluating a zero using Newton's method. So here's our example. We're going to approximate the zero of f of x is equal to x to the fifth plus x minus 1 to within 0.0001 of the true value. So since we're using Newton's method, we should try to remember what was the formula for Newton's method. So the formula that we had was we said that x sub n plus 1 is equal to x sub n minus f of x sub n divided by f prime at x sub n. So remember, these x sub n's, these were our first approximation, and then that gives us the next one of x sub n plus 1. So, for instance, you could use x sub 2 to find x sub 3. So this is the formula that we had for Newton's method. So we're going to look at the calculator here. So what I have downloaded is this program called WabbitEmu. It's a free program that you can create your own graphing calculator simulation on either your computer, or this is even downloadable on, I think, Android devices. So you could try to download this if you don't have your own graphing calculator with you, but it works exactly the same as a regular graphing calculator. So let's go ahead, let's turn this on, and then we will go to y equals. Let's start to visualize what this function looks like for us to see where is a zero potentially located. So we can enter in the equation of this, and when we graph this, we see that this looks like the zero is probably close to 1. So when it comes to Newton's method, we want to make sure that our initial approximations are very good approximations. If our initial approximation is very, very far away, there's the possibility that Newton's method might not get close to the zero that we're looking for. So in this case, we could start out with our initial guess would be 1. So if we go back to y equals, below this, I'm going to put in the derivative of this, because if we look at Newton's method, this requires us to not only have the function but also the derivative. So to program the calculator, I'm going to enter in the derivative, which is 5 times x raised to the 4th plus 1. So now that we have this, the function and the derivative, we can now go back to the main screen. And this is going to now start to use something that you might not have used on a graphing calculator before, is this ability to store information and then use that to store more information. So we're going to want to store in our initial guess of 1, and we're going to store this into the variable x. So we use that STO with the arrow button to store this, and we press enter. And so this pops out the number 1. That was our initial guess. Now we're going to type in Newton's method. So Newton's method, we said this is going to be the x value, and then we're going to subtract off what the function is. So we entered our function into y1. So you're going to go and press the vars button. So the vars button will introduce this menu. You go right over to y vars and you choose the function option. You see that you have the option now of putting in y1, which is where our function was stored. So press enter. And then I want to divide this by the derivative. We put the derivative into y2 in our y equals area. So we're going to, again, press the button vars. We go over to y vars, press function, press enter, and then you go down and press y2. All of this is going to be stored into the variable x. So this allows us to do this computation and say that the result of this becomes my new approximation. This is basically saying our x2 is going to be evaluated this way. So once you have this, you press enter. And so this gives us a next approximation of x2 is equal to 0.8333, and so on and so forth. Okay. So if you want to run the approximation again, you just simply press the enter button again. Now our next approximation is going to be 0.7643821157, and so on and so forth. So notice we seem to be getting at least a little bit closer, right? The jump from 1 to 0.833, okay, a little bit bigger than the next one. So we'll repeat this because we still aren't confident of where our approximation is going to be. So if I press this again, notice that my x4, my next approximation, is 0.750224867, and so on and so forth. So if we notice at this point, we have the number 0.7. 0.7 is repeating in both of these instances, and then the next decimal seems to be off, but at least it seems like the first decimal point might be 0.7. So let's repeat again and see what happens. Notice now that our next approximation is 0.75487777018. So now looking at previous ones, we should be pretty convinced that our true zero of this is going to start with 0.75. Because that amount is repeated, we should feel confident that moving forward, that will continue to repeat. Now, the next decimal is going to be different, so I'm not quite sure, but I'm already within the 0.001 of this, but I need to get within 0.0001, so I'm going to have to repeat this another time. Now, by repeating this, the next step, we see that our next approximation is 0.7548776662. So notice if we look and compare this to the previous approximation, we have a whole bunch of these values are repeated. So we can now be very confident that our zero is going to be approximately 0.754877, which brings us within the desired range that our error had to be within. So you could repeat this again if you would like and see that indeed this whole amount is indeed the desired accuracy of this. And so now our calculator can't go further than this. So just pressing enter over and over again will do nothing for us. So this is how we can use our calculator to quickly calculate Newton's method without having to do it by hand.